Hello everyone, my name is Avant Mehta and I have a question for you. Do you recognize the object shown in this picture? I'll give you a second to think about it. After all, it hasn't been in the news recently, considering it was launched in the same year that I was born. Nonetheless, it definitely was in the news, but for all the wrong reasons. This is the Mars Climate Orbiter. It's a space probe that costed NASA over $125 million to build, and every attempt was made to design and build this probe correctly. The navigation team at the Jet Propulsion Laboratory used the metric system while designing this probe. However, Lockheed Martin, the company which built the probe in Denver, Colorado, provided the acceleration data using the English system of units. Due to this mismatch in units, the probe missed its intended orbit and crashed into the Martian atmosphere. And this brings me to one of my favorite topics in the world of science and math, and that is quantities and units. In this video, we will look at the base units, derived units, prefixes for units, and vector and scalar quantities. Along the way, I will have some quizzes for you, so buckle up. So, what are quantities and units? A quantity is simply an amount of something, and it consists of a number and a unit. The number of that quantity is more accurately known as the magnitude. For example, we could measure the properties of matter, such as temperature, density, and volume, and express these measurements as quantities. The number indicates how many or how much, and the unit describes the scale of measurement. One way to define a unit is that it is a quantity chosen as a standard in terms of which other quantities may be expressed. Another example is that when a distance is reported as 5 miles, the quantity has been expressed in terms of miles, and the numerical value is 5. The unit that is associated with the number changes the interpretation of the quantity that is being measured. For example, 5 inches, 5 feet, and 5 miles are all very different distances because of the units that are associated with each numerical quantity. Moreover, reporting a numerical value without a unit renders that quantity meaningless. We need both the number and the unit to be included in order to fully express a quantity. Now that we have established that we need units in our system, which ones do we use? Well, there are so many of them. Thankfully, we do have a well-defined system of quantities and units. This is known as the International System of Units, or SI for short. It was established in 1960. This system consists of two classes of units: base units and derived units. Take a look at the 7 base units here. The beauty of this entire system is that it only requires the 7 distinct base units you see on your screen right now to derive any other unit. Now, I have a short quiz for you. I want you to pause the video for a minute here and guess the names of the base quantities that these units correspond to. I think you can get at least 4 of them. Ready? Go! Great, hopefully you've got a few of them. Let's review them together. I'm sure you've heard of the first 3 before. These are length in meters, mass in kilograms, and time in seconds. The other units are ones I'm sure you will learn in your science classes, and these are electric current in amperes, thermodynamic temperature in Kelvin, amount of substance in moles, and luminous intensity in candelas. Now it's great that we have these 7 units at our disposal, but this isn't nearly as many units as we truly need. The other units we have are called derived units because they can be written in terms of the base units. Let's take a look at the defining equation for a very basic derived quantity, and that is speed. The basic equation for speed is distance divided by time. As you can see, the right-hand side of this equation entirely consists of base quantities. Remember, we just learned that distance and time are 2 of our 7 base quantities, given that distance is one of the forms of length. Using this equation, we can derive the units of speed. The numerator of the right side is measured in meters, and the denominator of the right-hand side is measured in seconds. Hence, we find that the units of speed must be meters per second. So that's great. We just derived a unit from the base units. Now let's step it up a notch. Let's derive the unit for force. Have a look at the equation here. It shows us the very definition of force, and that is that force is the rate of change of momentum with respect to time. Here, momentum is denoted as mv, which is mass times velocity. Since the rate of change of velocity with respect to time is acceleration, we can say that the right-hand side is equal to ma, or mass times acceleration. Thus, we find that the net force is equal to the mass times the acceleration. This equation here is known as Newton's second law of motion, and it's one of the most well-known equations in physics. Using this equation, we can follow a similar process as we just did for speed. We write out the units that we know, that is, mass is measured in kilograms, and acceleration is measured in meters per second squared, or meters per second, if you will. Multiplying these together gives us the final result. The unit of force in SI units is kilogram meters per second squared. This unit is commonly known as a Newton. It is named after Sir Isaac Newton, one of the founding fathers of classical mechanics, a person whom I just so happen to share a birthday with. Now for our final case, I want you to work out the expanded form of the derived unit using the same type of dimensional analysis we just performed. So grab a piece of paper and a pen. The quantity I want you to work out the unit for is energy. First, write down any correct equation you've learned for energy, and then replace the known quantities with base units. If the quantities you have on the right side are not base quantities, you will have to dig a bit deeper and rewrite that quantity in terms of more quantities until you are down to only base quantities. So pause the video now, spend about 2 minutes, and find the full derived unit for energy. I'll wait for you. Alright, so if you have been able to find out the full unit for energy, then well done to you. If you're looking for a hint, here it is. One of the basic definitions for energy is that it is what is transferred when a force moves through a distance. That being said, the corresponding equation for energy is force times distance equals energy. So if you haven't been able to find the full form of the derived unit of energy yet, then pause the video here, spend about 2 minutes again, and see if you can find it now using this hint. So since we know that force can be written as kilogram meters per second squared, and distance is measured in meters, it follows that the unit of energy is kilogram meters squared per second squared. Now that sounds a bit wordy to say all the time, so we give these common units nice and short names. The unit for energy is commonly known as a joule. Let's say one day your friend asks you to measure the width of a strand of hair. You pull a microscope out of your pocket, and after tediously measuring a strand of hair, you finally find the width of this hair being this much. However, the only unit you know how to use is a meter. Do you just tell them that the distance was 0.00005 meters? That sounds awfully long, doesn't it? Surely there's got to be a more efficient way to express the length while still using the metric system. Thankfully, you watched my lesson on quantities and units, and you know that you can simply use the most appropriate prefix that makes it so much easier to express the quantity. The most commonly used prefixes are milli, which means 10 to the minus 3, and kilo, which means 10 to the third power, or 1000. Each prefix is said before the name of the unit. It acts as a modifier to that unit, since it changes the value of the unit by the corresponding factor. For example, in this case, you know that the quantity here is equal to 50 times 10 to the minus 6 meters. You can then look up the value of 10 to the minus 6 in this table to find out that that corresponds to the prefix micro. Now you can tell your friend that your strand of hair is 50 micrometers long. And that sounds so much more elegant, doesn't it? In this part of the lesson, we'll talk about vector and scalar quantities. These are two categories of quantities, and they're distinguished from each other by their definitions. A scalar quantity is fully described by a magnitude alone. On the other hand, a vector quantity needs both a magnitude and a direction to be fully defined. So what does that mean to us? Well, let's have a look at some examples of pairs of quantities that share the same unit, but where one is a scalar since it does not have a direction, and the other one needs a direction, hence it is a vector quantity. First, we have displacement and distance. Here, the quantity 8 kilometers and 8 kilometers east have the same magnitude and same unit. But displacement is a vector quantity since the direction was also defined. And here we have the same idea applied for speed and velocity. Velocity is a vector quantity since it requires a direction to be defined, but the quantity speed does not require a direction to be defined. Now I have a short quiz for you. Look at the table over here. I want you to fill in the blanks in the table that relate to whether the quantity is a scalar or a vector quantity. I've completed the first two rows for you as an example. The first is velocity, an example of which is 10.2 meters per second forwards. It is a vector quantity since the direction was defined as forwards. The corresponding scalar quantity is speed, since if there was no defined direction, it would just be the magnitude without the direction, and that is speed. Next, we have area, an example of which is 5 square meters. This is a scalar quantity since no direction is defined, and in fact you cannot attach a direction to an area since there is no quantity that acts as a corresponding vector quantity for area. For the next 4 rows, I want you to think carefully about whether the example of the measurement includes a direction or not. Ready? Go! Alright, let's have a look at the completed table. The third row was an example of displacement, since the direction was defined as eastwards in the example measurement. Thus, it is a vector quantity. As we saw earlier, the corresponding scalar quantity for displacement is distance. Next up is 5 meters per second. No direction was defined, so the logic here is very similar to that of the first row. The quantity is speed, which is a scalar, and the corresponding vector quantity is velocity. Next, we have 9.81 meters per second squared downwards. This is an example of acceleration, and since the direction was defined, it is a vector quantity. However, acceleration is a vector quantity that does not have a corresponding scalar quantity. Next, we have temperature, an example of which is 25 degrees Celsius. This does not have a direction, so it is a scalar quantity. Since it is not possible to attach a direction to a temperature, there is no corresponding vector quantity. This concludes my video on quantities and units. I hope that through this video you were able to gain an insight into the importance of using units correctly, gain a basic understanding of the 7 base units, and understand how the units for some of the derived quantities come to be. My name is Avant Mehta, and thank you so much for watching my video.